Good afternoon, everyone. My name is Seung Lee, and I am from Intelligent Neuroengineering Laboratory in Korea University. Today, I will present my research on the neurophysiological effects of white noise on working memory performance. Working memory is a brain system that temporarily stores and manipulates information needed for complex cognitive tasks. Defection of working memory may lead to learning disabilities and reading impairments. Many studies are being conducted to enhance working memory performance through specific stimuli, such as cognitive training, transcranial electric stimulation, and auditory stimulation. Among these methods, auditory stimulation, such as white noise, has the advantage of high accessibility, as it can be seamlessly incorporated into daily lives through passive listening. Recent studies suggest that white noise at 65 decibels can improve working memory performance in neurotypical adults. However, most of the existing studies have focused on working memory performance with limited neurophysiological evidence to support the observed effects. Modulation of working memory performance can be observed through electroencephalography, supported by extensive evidence. Typically, working memory modulation induces changes in theta and alpha oscillations. Each activity has a different meaning, and these activities can be measured in the central region of the brain. Therefore, in this study, we aim to investigate the neurophysiological effects of white noise on working memory by analyzing central EEG activity in healthy individuals. 20 healthy university students participated in the experiment. All participants were free from any neurological or psychiatric conditions that could have influenced the findings. Tubac test was used for working memory tasks. Tubac test assesses working memory by presenting a series of number stimuli, requiring participants to identify whether current stimulus matches the one presented 2 steps earlier, which is target stimulus. Each participant completed 2 blocks of the Tubac test with and without white noise. A series of number stimuli were presented randomly for 500 milliseconds with an interstimulus interval of 1,500 milliseconds. Wrong, missed, and multiple responses were considered incorrect, and target stimulus were presented in 30% of the trials. To avoid learning effects, we used counterbalancing method, and each participant completed a short practice session consisting of 10 trials. The practice session was repeated until 100% accuracy was achieved. To evaluate working memory performance, we calculated the accuracy of the Tubac test, which is the percentage of correct responses, and reaction times, which is the average time from stimulus onset to response. To further explore the influence of response correctness, reaction times were separated for correct and incorrect responses. EEG was recorded during the Tubac test using a smartphone's device, which allows simultaneous white noise presentation and EEG recordings. The device has 4 electrodes in each ear and 3 electrodes on the scalp, which is located in the central lobe. Data from 3 participants were excluded due to severe noise contamination. For the remaining 17 participants' EEG data, a bandpass filter was applied between 0.5 to 50 Hz with 60 Hz notch filter. And artifact subspace reconstruction was used to remove ocular and muscle artifacts. Remaining artifacts were removed through independent component analysis. The cleaned EEG data were then segmented from -500 to 1,500 milliseconds relative to stimulus onset. Wrong, missed, and multiple response trials were excluded to avoid inclusion of accidental errors, and central channels were used in the analysis. Since brain activity differs when errors are made during working memory tasks, the data were divided into all correct and incorrect tiles for analysis. Spectral power for each segment was calculated using the short time Fourier transform method with a 500 millisecond Henning taper window and the frequency range of 0.5 to 50 Hz. Power spectrum of each segment was averaged after applying baseline correction to the pre-stimulus period, resulting in event-related synchronization and desynchronization pattern maps across 5 frequency bands. For statistical analysis, we employed non-parametric techniques due to the non-normal distribution of the data. The Wilcoxon-signed rank test was used to compare the working memory performance and quantified ERD-ERS. And non-parametric permutation-based Wilcoxon-signed rank test was used to compare ERD-ERS pattern maps. In comparison of the working memory performance, there was no significant differences in accuracy or reaction times between the two conditions, and it was nearly identical. However, in both conditions, reaction times increased significantly during incorrect trials compared to the correct trials. The longer reaction times observed in incorrect trials suggest that participants experienced uncertainty or encountered difficulty in retrieving information. The following results present the ERD-ERS pattern maps across each condition. For the differences in the ERD-ERS pattern maps, only statistically significant areas are highlighted, while non-significant areas are marked in green. In all trials, strong ERS patterns in theta band were observed in both conditions, and these ERS patterns appeared weaker in the white noise condition. In the correct trials, strong ERS patterns in the theta band were also observed in both conditions, and similarly, the white noise condition showed the weaker ERS patterns compared to the no sound condition. The quantified ERD-ERS results for all trials also indicate that the theta band ERS was significantly weaker under the white noise condition, as well as for correct trials. In working memory tests, theta ERS is associated with memory encoding and retention, intensifying with increased task demands and cognitive effort. Therefore, the weaker theta band ERS in the white noise condition suggests that the cognitive load was lower and less effort was required to achieve correct answers in the white noise condition. In the incorrect trials, both conditions showed a strong ERS patterns in the theta band, but no significant differences were observed between the two conditions. However, white noise condition showed a strong ERD patterns in the alpha band compared to the no sound condition. The quantified ERD-ERS results for incorrect trials also indicate that the alpha band ERD was significantly stronger under the white noise condition. In working memory tasks, alpha ERD is associated with the process of information retrieval, and stronger ERD responses are observed as task difficulty increases to facilitate more efficient retrieval. However, if the task becomes too difficult, ERD responses may weaken, which could indicate an abandonment of retrieval attempts. Therefore, the stronger alpha ERD observed in the white noise condition may indicate that participants attempt more efficient retrieval when they were unable to recall the information. In contrast, the weaker alpha ERD in the no sound condition may indicate that participants abandoned their retrieval attempts when they were unable to recall the information. In conclusion, there was no significant difference in working memory performance between the white noise and no sound conditions. However, in the white noise condition, significantly weaker theta ERS responses were observed in both all trials and correct trials. Despite demonstrating the same working memory performance as the no sound condition, the white noise condition indicates a relatively lower cognitive load and less effort was required to achieve correct answers. Therefore, we propose that white noise reduces working memory load and facilitates correct responses with less effort. Additionally, in incorrect trials, the white noise condition exhibited stronger alpha ERD responses compared to the no sound condition. This indicates that the reduced cognitive load in the white noise condition enabled participants to retrieve information more efficiently when they were unable to recall the information. In contrast, the relatively high cognitive load in the no sound condition may have caused participants to abandon their retrieval attempts when they were unable to recall the information. In this study, the participants were predominantly in their early 20s and all possessed a high level of education, which may have introduced bias into the results. To improve the generalizability of the neuromodulatory effects of white noise, future studies should include participants from a wider age spectrum and educational backgrounds. Furthermore, this study only employed a single two-back test. Future research incorporating varying levels of cognitive load will be required to better assess the potential load-reducing effects of white noise. Thank you for listening.